Hello everyone. Now let's see OFDM system design problem. So the problem number 12.4 taken from this Andrea Goldsmith. So considering OFDM system, the total bandwidth of the signal B equal to 1 megahertz, and assuming the single carrier system symbol time TS is equal to 1 microsecond, that is nothing but 1 by the total bandwidth. The channel acts as a maximum delay spread of Tm given 5 microsecond. So with the Ts 1 microsecond, Ts 1 microsecond, Tm given Tm delay spread, the maximum delay spread of Tm given as 5 microsecond. There would be clearly say severe ISI because Ts lesser than Tm, that is the Tm value much greater than the Ts, so there would clearly be severe ISI. Assuming that the OFDM system M-array QAM modulation applied to each subchannel, that M-array QAM modulation subchannel modulation used in OFDM system to keep the overhead small. The OFDM system uses n equal to 128 subcarriers to mitigate the intersymbol interference. Therefore, the Tn is calculated. It's nothing but n times Ts. It's nothing but 128 into 1 microsecond. So the NTS nothing but 128 microsecond. The length of the cyclic prefix set to mu. The length of the cyclic prefix set mu given as 8. Okay, the length of the cyclic prefix 8 sample. To ensure no ISI, ensure that there is no ISI between the OFDM symbol because it satisfies the condition 8 greater than Tm by Ts. For these parameters, so we are going to calculate the subchannel bandwidth, total transmission time associated with the each OFDM symbol, the overhead of the cyclic prefix. Other than the data, how much the overhead, extra overhead. Finally, we are going to calculate the data rate of the system assuming m equal to 60. Okay, let me draw the OFDM subcarriers with the frequency. So this is the OFDM subcarriers. Here the total bandwidth of the signal is given, that is B is equal to 1 megahertz. We find the sampling time Ts. The Ts is nothing but 1 by B. 1 by B is nothing but 1 microsecond. Okay. So by substituting the value of B, then we get Ts is equal to 1 microsecond. The channel delay spread, as I said, Tm 5 microsecond. The coherence bandwidth BC, it is denoted by BC, nothing but coherence bandwidth, that is nothing but 1 by Tm delay spread. It's nothing but 1 by Tm 1 by 5 microsecond. So 1 by 5 microsecond, the value of the channel bandwidth 200 kilohertz. Okay, so the BC is nothing but the channel channel coherence bandwidth. So with the Ts 1 microsecond, Tm 5 microsecond, so that is the Ts much lesser than Tm, so severe ISI. Hello everyone, this is Deepa. Okay, we are going to see problem now related to OFDM system design. So the problem is taken from the reference Andrea Goldsmith wireless communication. Problem given, given problem OFDM system with the total bandwidth be 1 megahertz, assuming Hello everyone, this is Deepa. We are going to see problem related to OFDM system design. This problem is taken from the Andrea Goldsmith wireless communication. Okay, so given these parameters, OFDM system parameters, we are going to calculate the channel bandwidth, total transmission time associated with each OFDM symbol, the overhead of the cyclic prefix, and the data rate of the system assuming m equal to 16. Let me draw the OFDM subcarriers with the frequencies. So the number of subcarriers with the frequencies. So the total bandwidth given 1 megahertz. The total bandwidth of the system, the OFDM system is given. So 1 megahertz. We find the sampling rate from given 1 by b, nothing but ts. That's so sampling time ts is equal to 1 by b, that is 1 microsecond. Okay, the channel has maximum delay spread of tm given as 5 microsecond. So the 5 microsecond delay spread. Okay, so the coherence bandwidth. So the coherence bandwidth, it is denoted by BC, that is 1 by delay spread, 1 by Tm. It's nothing but 200 kilohertz. So given value of Tm, the coherence bandwidth BC is found. So with Ts 1 microsecond, Tm 5 microsecond, so the condition, the Ts less than the Tm. So there would clearly be severe ISI. Okay, because Tm much greater than the Ts, so there would clearly be severe ISI, intersymbol interference. Assuming the OFDM system with the M-array QAM modulation, so M is the number of symbols in constellation. Okay, so we have n equal to 128. Yeah, we have n equal to 128 subcarriers. Now let us draw this spectrum again with subcarriers F0, F1 and up to subcarrier with 128 subcarriers. So this is actually 127 subcarriers. So given NTS here, n 128 subcarriers, Tn, calculate Tn. Tn is equal to n into Ts. So n times n times of the Ts here is nothing but 128 into 1 microsecond. It's nothing but the Tn is equal to 128 microsecond. Now let's see the length of the cyclic prefix given as given as 8. So therefore the length of the channel channel is expressed as Tm by Ts. Tm is nothing but 5 microsecond and Ts 1 microsecond. So we get 5, though the length of the channel is 5. So the length of the cyclic prefix 8, it's given in question now, and the length of the Cp and length of the channel. So now let's see the relation now. The length of Cp, the length of Cp greater than or equal to length of the channel. So now this is the condition. Now we'll now substitute 8 greater than or equal to 5. So the condition is satisfied. The condition is satisfied. So now let's proceed. Satisfied. So now we find first the subchannel bandwidth. To find the subchannel bandwidth, so Bn nothing but the total bandwidth divided by number of subcarriers to find the subchannel bandwidth from the total of 128 subcarriers. So 1 megahertz by 128, this is nothing but 7.812 kilohertz. Or another method using this formula, Bn is equal to 1 by Tn. 1 by Tn, that is nothing but 1 by 128 microsecond. You get same answer, 7.812 kilohertz. So use formula for finding subchannel bandwidth with n number of subcarriers, or using the Tn value. So now Bn, its subchannel bandwidth much lesser than Bc, that is 7.812 kilohertz, much lesser than the coherence bandwidth. So what is coherence bandwidth? It's nothing but 200 kilohertz. So negligible ISI. Okay, so the condition satisfied because the Bn much lesser than the coherence bandwidth, and because of the larger coherence bandwidth, no ISI. Okay, no ISI. So the condition also satisfied. Each of the subchannel, so therefore each of the subchannel undergo flat fading. Okay, flat fading. Okay, now let us find the transmission rate. The second one, the transmission for each OFDM system, the total transmission time. We are going to find the total transmission time. So what is T? Okay, so you all know the OFDM symbol structure. It consists of the cyclic prefix and the actual data, IFFT data. So the God interval GI, and here the actual data nothing. Here I write IFFT data. Okay, IFFT data. So this is structure of the, this is the structure of the OFDM symbol. So God interval. Okay, so the God interval here, what is the time, what is the transmission time for this actual data? It's nothing but Ts. So here God interval size nothing but cyclic mu into Ts. Okay. So the total transmission for each OFDM symbol, it is denoted by T equal to sum of these two. Okay, so here IFFT data, the size of this IFFT data is nothing but Tn. It is actually it is denoted by Tn. Okay, so mu into Ts plus Tn, sum of these two. So we get the total OFDM symbol time along with cyclic prefix, nothing but T equal to cyclic prefix length 8 into Ts 1 microsecond plus the IFT data size nothing but 128 microsecond. So we get T equal to 136 microsecond. So far we calculated the subchannel bandwidth 7.812 microsecond, and the the total transmission uh, for each OFDM symbol is 136 microsecond. Okay, now let's see the overhead of the cyclic prefix. The overhead of cyclic prefix. So what is the amount of time dedicated for cyclic prefix? Other than the IFFT data, how much data means the cyclic prefix sending? Okay, so that is the extra overhead associated with the cyclic prefix, mm, measured uh, measured by 8 microsecond divided by 128 microsecond. Okay, so we get 6.2. So the overhead of the cyclic prefix measured in percentage 6 point so as per calculation 6.25 percentage. Okay, 6.25 percentage. So the overhead of the cyclic prefix in percentage 6.2. Okay, now let's see the data rate calculation. So fourth one, the data rate of the system. Okay, the data rate of the system, it is denoted by RB. So what is RB? Since 16 array QAM modulation used, so the assuming M is nothing but 16. Okay, M is nothing, M given 16. Okay, so here 16 array QAM modulation in this OFDM system, that is nothing but 2 power 4. The 2 power 4 is equal to 16. So that is 4 bits are required to specify one symbol. Okay, so the system transmits 4 bits per subcarrier. So the system transmit 4 bits per subcarrier for every t seconds. So every t seconds. So the t corresponds to the total. This is the t. The total time for OFDM symbol corresponds to the total transmission of the OFDM symbol. It is calculated. It is found, right. So what is the value of t? Is 136 microsecond. 136 microsecond. So now let's see the RB for given 16 array QAM OFDM system. So RB is equal to, so 4 bits required, right, every per subcarrier. Okay, 4 bits are required to specify one symbol, and 4 bits. So how many symbols we have? To 128 symbols. 128 symbols. The total transmission happen in 136 microseconds. So therefore 4 into 128 divided by 136. Okay, 136 microsecond. So 10 power minus 6. This is nothing but bits per second. Okay, so the data rate is measured in bits per second. So RB is calculated. What is RB? 4 into 128 divided by 136 microsecond. That is nothing but 3.76 megabits per second. Okay, so given OFDM system design problem, the sub-channel bandwidth, the total transmission for each OFDM symbol, the overhead of the cyclic prefix, and the data rate of the system is calculated. Thank you.